Hello, chemistry. As I was sifting through the various online tutorial videos working with stoichiometry, I finally decided that I would put together my own video because I really want to emphasize the, kind of general philosophy of stoichiometry. Some of the online videos focus too much, I think, on just doing practice problems. And the problem with stoichiometry is that there are all sorts of um, different designs of stoichiometry problems that you can come up with, and you could memorize them all, but there literally would be thousands of stoichiometry problems that you'd have to try and memorize, and it's better off if you just kind of understand how to do it, and then whatever problem you're faced with, you can logically put together an algorithm of how to solve them. So, although I say don't just work through examples, I'm going to start with an example. So let's start with a balanced chemical equation, and that is a fundamental part of doing stoichiometry. Is that this all is based off of having a balanced equation to start with. If you don't have a balanced chemical equation, if your formulas aren't correct, then all of this is going to be a bit useless. So I can look at this equation. So this is sulfuric acid and potassium hydroxide reacting to produce potassium sulfate and water. In our classification of reactions, this would be a reaction involving an acid and a base producing a salt and then water. It's a neutralization reaction. It's a form of double replacement reaction. And it's one that requires a little bit of thinking because the hydroxide group and the sulfate group have different oxidation states as groups, which causes the potassium atoms and the hydrogen atoms to end up bonding in different numbers as we work through the reactants to the products. So it's a nice example to use, not too complicated. It's something similar to some reactions we'll do in lab. So the questions that we get, and this is on the paper that I handed out in class titled, kind of the types, it was the introduction to stoichiometry, the types of essential stoichiometry questions that you'd get answered. So the question might be, I have a certain mass of sulfuric acid, and I want to know how much mass of potassium hydroxide I need. So we'd call that a mass to mass calculation. And I could do that between two reactants. I could do that between two products. I might have a volume question. So this H2SO4 is going to be a solution. It's going to be at a certain concentration. So we might have so many liters of sulfuric acid at a concentration of so many moles per liter. That's a common measure of concentration. Is, you might have 5 molar, which means that you have a concentration of 5 moles of sulfuric acid dissolved in 1 liter of water. So we could say, hey, I have the solution of sulfuric acid. How much potassium hydroxide, which could be a solution or it could be a solid that you need to dissolve into solution, how much potassium hydroxide do I need? You might say, I have liquid water. Liquid water has a certain density. What volume of water would be produced from certain reactants? Well, then I'd have to say, well, what's my mass of water? What's the density of water? And then I could get the volume of water. If one of my reactants was a gas, another equation that we may look at here is just the simple reaction of hydrogen with oxygen to produce water. And you might say, well, if I have a certain volume of hydrogen gas in liters, how much water will be produced? And since we know gases are compressible, that number may depend on the pressure or the temperature of the gas. We've already mentioned something called standard temperature and pressure, which is 0 degrees Celsius or 273 Kelvin. and at a pressure of 1 atmosphere. If the gas is not at that, then we'd have to do some sort of a calculation involving the pressure and the temperature um, in doing that. So you can't memorize necessarily all of the possible variations of a stoichiometry problem. What you need to do is learn how to do a stoichiometry problem regardless of what you're given. And it's a matter of you've got to reach into the toolbox. You've got a toolbox and it's going to be filled with a hammer and a screwdriver and some sandpaper and a wrench. And the hammer might represent a molar mass. The screwdriver might represent a concentration. The sandpaper might represent a density. And what was the other tool I had? I don't even remember. Pliers or a wrench. That might represent volume of a gas at standard temperature and pressure, 22.4. So you look into your toolbox and you pluck that out and you use the right tools and you solve the problem. The one tool that almost always comes into play when you're doing one of these things, particularly when you're working at comparing one substance to another. Sometimes if you're just saying, oh, I want to make a solution of sulfuric acid, and I want to make 5 liters of solution, and I want it to be a 1 molar concentration. How many grams of pure sulfuric acid? This isn't a great example because in my life I've never worked with pure sulfuric acid, but how many grams would I need to make that particular solution? That is a case where you're still going to use moles because you have to know exactly how much you have, but you're working with only one substance in that case. So that's like a little subset of chemistry math. But if we're doing full stoichiometry, which is I have this much of this substance, what's the amount of this substance? What's always going to come into play is the mole ratio. Okay, that has to be in the back of your mind, that somewhere in your calculation, in the middle of it, is going to be using the mole ratio. Mole, 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 mole. The commercial that's like free, free, for free, free, free. Well, stoichiometry is mole, 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 mole. So let's take a question that of 23 grams potassium hydroxide. How many grams of potassium, got ahead of myself. How many grams of potassium sulfate will I produce? This is pretty common. This is called a mass stoichiometry problem. If you're looking for extra help videos and you go to YouTube, you can search mass stoichiometry and you'll get a whole bunch of examples that look like this. So that's the question. So over on the left side of my thought process, I'm going to write my known value, 23 grams KOH. Over on the left side of my thought process, I'm going to end up with an equal sign and a blank for me to hopefully fill in that says grams K2SO4. And in the middle, I'm going to put moles K2SO4 over moles KOH. I'm just telling myself that I am going to need the mole ratio from the chemical equation. Anytime I go from one substance to another, the only way I can make that jump is with a mole ratio out of the chemical equation. In fact, I can go up right here and pull that mole ratio out right now, so I don't even have to worry about it later. 2 moles potassium hydroxide to 1 mole potassium sulfate. So that's there. Written as a fraction. And so there's this question then of why did I put KOH on the bottom and why did I put K2SO4 on the top? And there's a little bit of integer rules, algebra rules that come into this. Hopefully you know that you can multiply 2 times 3. It's 6. That's great. But the same expression could be written 2 over 1 times 3 over 1. way overkill, but that's reasonable. And if you did that, you multiply everything across the top, so 2 times 3 is 6. You multiply everything across the bottom, 1 times 1 is 1. We get 6 over 1, which equals the 6 that we expect to get. Hello, Captain Obvious. But what about if we did, let's do 4 divided by 6. Well, 4 divided by 6, which sometimes, you would see it written this way, the old school division sign. That is the same as saying 4 over 1 times 1 over 6. And this is an important kind of algebra thing or arithmetic thing, that multiplying is the same as, no, I did that wrong. Division equals multiplying by the reciprocal. And division is the same as multiplying by the reciprocal. So 4 times 6 is 4 over 1 times 6 over 1. 4 divided by 6 is 4 over 1 times 1 over 6. So when you look at the math going into this, we are doing all multiplications, and we really want everything as a fraction. So even this simple number 23 I have, I'm going to put it over 1. And so what you notice in doing this is that I have the substance potassium hydroxide on the top, and now I have the substance potassium hydroxide on the bottom. So really what I have is KOH divided by KOH. And yes, you can divide a substance by a substance. It's like if I have x squared over x, what does that equal? That equals x. You subtract the exponents, one of them cancels out. Well, what if I have x over x? Well, anything over itself equals 1. Anything over itself equals 1. So a unit over a unit, which in this case, the name of the substance is actually a unit like meters or liters or anything else, anything over itself cancels out. So if we want to get from potassium hydroxide to potassium sulfate, the potassium hydroxide has to cancel out somewhere and leave us at potassium sulfate. So I want KOH over KOH, which is why in the mole ratio, I write it as 1 over 2 and not the other way around, 2 over 1. But this brings up another problem, and that problem is that I can't cancel everything out with potassium hydroxide because I have grams here and moles here. So in order to link those two, I need a term that has these 2 units in it. And hopefully by this point we recognize that molar mass, grams per mole, is the term that we're going to link in the middle here. So I calculate it myself, potassium plus oxygen plus hydrogen, or I go to WebQC and I look it up, and I find that potassium hydroxide has a molar mass of 56.11 grams per mole. And again, I want grams on the bottom. Whoops. I want grams on the bottom. Why did I put equal signs? We're multiplying. I want grams on the bottom and moles on the top because I want the grams to cancel. And I ultimately want moles of potassium hydroxide to cancel as well and leave me moles of potassium sulfate. That's how I get from one substance to another, is get to moles, jump through the mole ratio, and then get out on the other side to whatever you need. So I look up the molar mass, potassium hydroxide, 56.11 grams per mole. So grams cancel, potassium hydroxide cancels, moles cancel, and now I'm at moles of potassium sulfate. I've made the jump from one substance to another, but I'm not there yet because I want grams, I need moles, I'm in the substance potassium sulfate, so I need grams and moles of potassium sulfate, which means I need its molar mass, which I've already looked up, is 98.08 grams of potassium sulfate per mole. And so now moles cancel, and look at the units I have left. Substance potassium sulfate, unit grams. Grams potassium sulfate. So at this point, I'm pretty confident that I have everything set up correctly. You know, when the units all cancel out and end up with what you want, it's a pretty good sign that you have set everything up properly. And so just like my fraction like this, multiply everything across the top. 4 times 1 equals 4. 1 times 6 equals 6. I do the same thing here. Multiply everything across the top. 23 times 1 times 1 times 98.08. So that is, I always do my math twice, and that number looked weird, but hopefully I get the same thing. 98.08. Yep, so 2255.84 divided by everything on the bottom. So 56, so 1 times 56.11 times 2 times 1, 112.22. And if you do all this in the calculator, I can actually do it all at the same time because PEMDAS lets me do it. So if I just do 23 times 1 times 1 times 98.08 divided by 1 divided by 56.11 divided by 2 divided by 1, I get 20.1. I look back at my original measurement, only had 2 significant figures, so I'm actually just going to leave it as 20 grams of potassium sulfate is my final answer. You say, does it make sense? Well, all right, so this is the point at which I have to stop myself here because what I realized after I recorded all this is, no, this does not make sense. I made a mistake. It happens, you know. That number is not correct, which means that that number is not correct, and why it's so important to go back and double check things. The molar mass of potassium sulfate is a whole lot heavier than that, 174.26. So here's a case of I have all of the work set up, so I don't necessarily have to go through and redo everything. And this is a great advantage if you really do organize your work on the page of when you do recognize a mistake, that you can just go back and fix the parts that you messed up on and don't have to redo the whole thing. So I'm going to fill in 174.26 here. I'm going to go back to my calculator and I can plug in all of the math again. 23 times 1 times 1 times 174.26 divided by 1 divided by 56.11 divided by 2. And now I get an answer of 35.7, which I'm going to take the 2 significant figures, 36 grams of potassium sulfate. And just because I don't have a whole lot of confidence right now, I'm going to do the math again, punch it into my calculator. Punch, punch, punch. I'm not as fast. Typing on the computer is on a regular calculator, but I get, ooh, good, same number. Pretty confident in this right now. Glad I fixed that. I could stop anywhere along the way if I really wanted to. You know, that is a full mass-to-mass stoichiometry problem written as what's called a dimensional analysis. There's a chemistry tutor online called Brightstorm, and they do this as what's called the picket fence model, where they instead of using multiplication signs and fractions, they use what looks like a picket fence. and you fill in the terms the same way, but you multiply across the top, divide across the bottom. But I could stop any place I wanted and use sort of the same thought process. What's another? I have another example to think of here. Get rid of all of this. Let's see, what if I have 21 grams of sulfuric acid, and I want to know how many moles of water that could produce. So same thing, 21 grams. Just get in the habit of putting it over 1 equals moles of water. And I know I'm going to need a mole ratio in here. Moles of water, my product on, or my answer on top, my given on the bottom. I'm going to go ahead and pluck it out of the equation, so it's 2 to 1. And notice that this actually is the answer I'm looking for. So all I need to do is get something that cancels grams and moles of sulfuric acid and leaves me at moles of water. And that's going to be the molar mass. And for sulfuric acid, that is 1 mole of sulfuric acid has a mass of 98.08 grams. So grams cancels, sulfuric acid cancels, moles cancels there, leaves me moles of water. And I can plunk this right into my calculator. 21 times 1 times 2 divided by 1 divided by 98.08. I totally did that wrong. Ugh. Figure out what I did wrong in the last one. I know I did it wrong. I'll go back and fix it here. 98.08 equals, let me double check my math, 21. Yep, so I still don't like that. See, I did the math twice, and I got 2 different answers. And using my computer calculator over here is not my favorite. So there we go. Now I got the same answer twice. So 0.43 moles of water. So I have about, a fifth of a mole, maybe, about a quarter of a mole of sulfuric acid at a 2 to 1 ratio. I've got a little under a half a mole of water, so that makes sense. Okay. Moving on to one last example then. What if I had 27 liters of hydrogen gas at standard temperature and pressure? No, we're not going to worry about conditions not at standard temperature and pressure at this point. Equals how many grams of water produced? Same thing. 27 liters of hydrogen gas over on this side, write it as a fraction, equals grams of water. I know somewhere in the middle I'm going to need a mole ratio, so it's 2 to 2, which is 1 to 1, so it's 1 mole water. Put my answer on the top, my given on the bottom. And I don't really have a way to get from liters to grams. Liters to grams, mass and volume would require me to know a density. I don't know the density. I'd have to know pressure and well, I guess I do know pressure and volume and stuff, but I'd have to do all sorts of things to determine the density of the gas. But I do know that there is the kind of known shortcut for getting from liters of a gas at standard temperature and pressure to moles, and that is the 22.4 liters per mole converter. And again, I look at that and I say, I want to get rid of the liters. I want to leave myself at moles. So I put that there. So liters is going to cancel, moles of hydrogen gas is going to cancel, leave me at moles of water. And then I need to get to the mass, so that's 18.02 grams and 1 mole for water, and that cancels the moles and leaves me at grams of water. So the math again, 27 divided by 22.4 times 18.02. And if you notice what I did there is I've just done this so many times, I realized the shortcut. And again, rounding to significant figures here, 22, 21.172, rounded to 22 grams. 27 times 1 times 1 times 18.02 divided by 1 or divided by 22.4 divided by 1 divided by 1. All the multiplies and divides by ones I can just ignore because that does nothing. So I just go 27 divided by 22.4 times 18.02 PEMDAS is wonderful, and that gives me the answer. What's kind of nice about doing that is also the, commutative, transitive principles, those all still apply. So I can go 27 divided by 22.4 times 18.02, get a number. I can go back to my calculator, and then I can do it backwards. 18.02 divided by 22.4 times 27. Anytime you can do a calculation forward and backwards and get the same number, that gives you pretty good reassurance that you plugged it into the calculator correctly. That's something that Mama Sucre taught me. So that's what you do. If you had, something where you needed to use density, you plug in, grams per liter, grams per milliliter, that becomes a conversion factor. If you needed to get to concentration, moles per liter, you'd plug that in. All the stoichiometry problems end up looking like these. You've got a mole ratio somewhere in the middle. You've got an unknown value you're trying to find. You have a known value, and you just plug in little fractions in the middle that allow you to move step by step from what you know to what you're trying to find. That's the basics of stoichiometry. You've got some practice problems out there to work on. Work through those, and we'll hopefully just build some confidence